Last time we looked at titration curves of monoprotic acids and monoprotic bases. Now we're going to look at polyprotics and their titration curves. One of the dominant features of polyprotics is they have more than one equivalence point, which is logical, of course, because these polyprotics usually have more than one acidic proton, or they can accept more than one proton if they're acting as a base. So here we have a graph of a polyprotic. Actually, in particular, just looking at the graph, we can say that this is a diprotic acid. Why do we say that? One, it's because we're starting at a low pH, so likely it is acidic, or it's definitely acidic, and the pH is increasing. Two, it's because I see pretty much two inflection points here, well, one inflection point here, and I see two sharp, more or less, curvatures which indicate equivalence points. And this is a prominent shape of a diprotic acid diagram. One other feature that is also comes up is that each mole of H plus shows as separate equivalence points. Now, in diprotics, yeah, you usually do see pretty much sharp enough curves or lines here at the equivalence to distinguish them. In triprotics, it's not always distinguishable in the third region, because our Ka is usually, Ka3 at least, is usually very small. But with Ka1, Ka2 for a diprotic acid, you can pretty much see sharp enough curves, lines here on the equivalence to distinguish that it's a diprotic. Also, at the equivalence, the same volume of added base is required to remove each proton from this diacid. So for example, if I need 25 milliliters to go from, so here we're splitting up these curves into two different curves. The first curve actually is pretty much starting from this point, and we're going to continue all the way to the first equivalence point and maybe a little bit slightly above. So what that curve is for this diprotic H2A becoming deprotonating, neutralized, and deprotonated as we're adding OH minus, and here we have the volume of OH minus being added. The H2A is becoming HA minus and water. So here I start off with H2A only, and I'm adding OH such that I'm producing, as my OH is the limiting reagent before the equivalence point, I'm producing some HA minus as the reaction is proceeding. Of course, we always treat these reactions as a complete reaction, at least for us in first year. Anytime we said we have a strong acid or a strong base as a reactant, just treat it as a complete reaction. Now, all of the H2A at the equivalence point, which is right there, has become HA minus because we have equal amounts of acid and base added. So they become zero in solution, H2A becomes zero, OH minus becomes zero, or epsilon, and everything gets converted into HA minus. Okay, now, before, when we were just doing a monoprotic, remember after the equivalence, we were having HA minus, let's say, and excess OH minus. And we used to say with monoprotics that we have two mixtures of two bases. Well, what you should notice here is that HA minus is actually not just a base, it's an amphoteric substance. It's not only a base because it has a negative charge, it also has a proton, so it acts as an ampholyte. And also in the presence of OH minus, if I add more OH minus to the solution, indeed this HA minus will act as an acid, and thus forming my next reaction, where HA minus, upon addition of OH minus, becomes deprotonated further into A2 minus. And this is where the second curve starts to take place. So here I have HA minus pure, and as I'm adding OH minus, that OH minus is going to be the limiting reagent in this case, removing the HA minus in solution. In this area, again, what do we have here? We have a buffer region, yes, where I have both species HA minus and A2 minus being produced, up until we get to this equivalence point where all of the HA has run out or has been neutralized. So we have 0 here, 0 OH minus, and everything has become A2 minus at the equivalence point. Of course, if I add more OH minus, then I have here on this end mixture of two bases, the A2 minus and some excess OH minus in solution. Great. So pretty much we actually have as if literally two monoprotics, if you will, type of weak acid titration. So this is the first, and if I start from here upwards, this would be my second. Okay, so one, and here is my second curve. Now again, one of the questions that arises is why does it require the same amount of volume to neutralize this first acid as it requires to neutralize the second acidity? So if I require 25 milliliters to reach the first equivalence point, I will also need another 25 milliliters to reach the second equivalence point. And it's actually very logical. Speaking of, remember how all of the H2A becomes HA minus at equivalence, right? So the number of N moles of H2A reacted will equal to the number of N moles of OH minus added at equivalence, which will also equal to the number of moles of HA minus produced. So whatever I have initially in my solution, that's going to be the amount reacted at the equivalence point for my H2A. And so in the second reaction, the number of moles of HA minus reacted at this equivalence is equal to the number of moles of OH minus added. Well, what is this NHA added, reacted? Well, that's just coming from this equation. And what is that amount? That's just coming from the H2A. So actually we have the same number of moles of H2A as we have NHA. So of course we need the same volume to neutralize this acid and the same volume to neutralize the H2A. So they require the same volume because they have the same number of moles in the solution. Anyhow, well, all you really need to know is that the first equivalence is equal to the second equivalence volume. Okay. Now let's look at a little bit more detail and a little bit more calculation of the pH points in a diprotic calculation. So here we have the H2A again reacting with OH in a one-way reaction. We always assume that the K reaction is complete. Hopefully it will be. And then the HA minus also then reacts with OH minus to produce A minus, and again in a complete type reaction by assumption. And we also suppose that reaction 1 finishes before reaction 2 starts. And that means that the K reaction 1 is greater than 100 K reaction 2. And actually in all of the general chemistry in this course for this first year, you always have separate reactions. We never take consecutive reactions together at the same time. We always take one reaction, it completes, it finishes, and then the other one starts. All right. Now, again, just looking at the curve, yes, we have two jumps, one here and pretty much one somewhere here. Actually, it should be more like there. I don't know why they put it on this end. I would have put it more on like that part right there. But anyhow, that's where it looks more straight. But we have two jumps, okay? So this is a diprotic curve, most likely. And so at this first jump, okay, this first straight line vertical, we will say this is V at equivalence 1. And at this vertical, here again, but at this vertical, we say it's V equivalence 2. Okay. Now, let's look at the different pHs and the different species. And of course, to get the pH, you have to look at the species present in each part. What do we have initially, right, at this point? Of course, you only have the H2A at the beginning, right? Okay, so if I only have H2A at the beginning, the pH, this is just an example with that. The pH will be the pH of H2A. So what is H2A? It's a diprotic acid, and you have to go back to the diprotics. And usually with the diprotic acids, they just act as monoprotic acids, especially if Ka1 is greater than 100 Ka2 for the second equation, which we said it always is for our cases. And so we treat this diprotic as a monoprotic acid. And then what do we have to do? Yes, the second part is we have to look at the concentration of this acid. Is the concentration of this acid greater than 100 Ka? If it's greater than 100 Ka, Ka what? Ka1, then we can simply use the equation which states, let me just go to this part, okay? So the equation which says pH equals half pKa1 minus half log the concentration of that acid. Under what validity conditions can we use this? This is when the concentration of the acid is greater than 100 Ka2. So that's at the initial where I've added 0 milliliters of NaOH. As I add more NaOH, okay, what happens? Yes, the H2A starts to convert to HA minus, right? The H2A starts to convert to HA minus. So we get some H2A and some HA minus in my solution, which is what? A buffer, right? If I have H2A and its conjugate base, that means I have a buffer-like or a common ion effect. What do I use to get the pH? Absolutely, you use Henderson. And indeed, this we call this area, the straight horizontal line, the buffer region. Okay? There's a particular value which is very important in the buffer region, which is when the HA minus equals to the H2A, which occurs at the half equivalence point. So if my equivalence point, the equivalence 1 is, say, 20, at volume 10, I will have my half equivalence, the equivalence divided by 2. Great. What is the pH then? Of course, the pH is pKa1. Okay, so automatically, actually, right away, without doing any calculation, if I see a diprotic, automatically at half equivalence, right, the pH equals pKa1, so you have this value point without doing any calculation whatsoever. Okay, so here again, my H2A is decreasing while my HA is increasing. My HA is increasing until all the H2A has been used up and has reacted, and all of it gets converted to HA minus. What is that? Yes, absolutely, that's at my equivalence point. Great, so what is the pH at this volume equals equivalence point? Well, what species do I have? I have HA minus. What is HA minus? Yes, it's an ampholyte. What is the pH of an ampholyte? The pH of an ampholyte is simply half pKa1 plus pKa2 for this particular ampholyte, HA minus, because this HA minus can react either as an acid or as a base. Okay, so I'm at this equivalence point right now. So now I have a new equation taking place. Now we have HA, which is gonna be converted to A2 minus. In this region, it's like another curve altogether, another type of monoprotic, if you will, titration. So HA now, as I add more OH minus, is going to become A2 minus. So what do we have? We have a region where I have both HA minus and A2 minus. At what volume? Yes. This volume is between, in this region, it's anywhere between the first equivalence and the second equivalence. So anywhere in between that, okay, we have both species, HA and A2 minus. We have both of these. At a particular value, which is 3 divided by 2V equivalence 1, which is, in other words, look at this. If this is half equivalence, and this is at the equivalence, another half equivalence, okay? So, and this is a third half equivalence, so this is 3 half equivalence points. So if my equivalence point is 20, my half equivalence is 10. So this is 10 milliliters and another 10 milliliters and then another 10 milliliters. So it's actually 30 milliliters would be my volume at V, which is 3/2 V equivalence 1. Okay, what happens at that volume right here, which is the middle point, the midpoint between V equivalence 1 and V equivalence 2, right in the middle there? Yes, that's when HA minus is going to equal to A2 minus. And so what's the big deal when that happens? Yes, the big deal is when these two species are equal to each other with Henderson, when I apply Henderson, because overall this region is more or less a buffer-like region, again in the horizontal area of it, the pH equals pKa2. And of course, I could have just put that right at the beginning without doing any calculation. So automatically at half equivalence and 3/2 V equivalence, okay, then I automatically can put 1 and pKa2. Also, again, even at this equivalence point, first equivalence point, that's a very easy calculation, just half pKa1 plus pKa2. So the calculation of this point is also very, very easy. So these are very easy points to calculate without, doing much further. Now, once I got to this area again, so I'm at the pKa2, I'm now also, I have both HA and A minus equal to each other. As I add more OH minus, more HA gets converted to A2 minus, and then have more A2 minus in my solution, more A2 minus, less HA, until all of the HA has run out and everything has gotten converted to A2 minus. So all the moles of H2A initially got converted to HA minus, and that eventually got converted to A2 minus. And now how do I get the pH? Well, of course, this is the pH of a dye base. And now we have to do the calculation of a pH of a dye base. What is the pH of a dye base? Well, this dye base acts as a monobase, hopefully. And usually we say that it does. This is valid. It acts as a monobase is if KB, KB1 is greater than 100 KB2. And then also if the concentration A2 minus is greater than 100 KB1, Then, and we watch out for dilution, then we can simply use this equation, which is pH equals 7 plus half pKa2 plus half log A2 minus. Now notice this is KB1, yet I use Ka2. Remember the KB1, when we want to do the calculation, we have to use the Ka2 value for its calculation. So what's the concentration of A2 minus? Well, A2 minus is simply the same amount of moles as my original acid. So CAVA, which is the moles of this acid, divided by the total volume. What's the total volume? It's the volume of the acid that I used, plus 2V at the equivalence, V equivalence 1. Why 2V equivalence 1? Why not just V equivalence 2? Well, remember, V equivalence 2 is twice V equivalence 1, 2 times the amount. Okay, so now I have the concentration. You simply substitute and you get pH. After this point, so after the second equivalence, when the volume is greater than V equivalence 2, I simply have OH minus in excess, as well as some A2 minus in my solution, and therefore my pH becomes excess OH minus. Okay. Now in the previous slide here, we just put some of the values which are easy to calculate, which is pKa1, half pKa1 plus pKa2, pKa2, these are automatic points which you should be able to put in. Okay, so we have the first equivalence and the second equivalence, a little bit more complicated to get the pH at the second equivalence, but it's simply 7 plus half pKa2 plus half log the concentration of A2 minus, which showed how to calculate it. Okay, this is a written example, no need to get into it really. All right. Now, what looks like a complicated thing, if I talk about it before titration, is actually very simple to talk about predominance domains after titration. So once we understand in a titration type diagram what species we have as my volume of base is changing, when I say volume of base is changing, I'm also changing the pH, right? So as my pH changes, the species that I have in my solution changes. All right. So instead of doing this vertical pH diagram, we can have what is, these are just pHs at different, what we just discussed at different points in my solution. So we can have a vertical, a horizontal pH diagram. Here we have vertically the pH in a titration. I'm just going to now put it in a horizontal way. Okay. So if I put it horizontally, so my pH is increasing this way. Here my pH is increasing upwards. Initially, which species do I have for a triprotic? Yes, I only have H2A, right? As I increase my OH minus, or as my pH increases, right? What species do I get to? Of course, at some point, we only get H2A. And so I go from H2A, I go from H2A, I start to produce HA minus. And as my pH increases further, I start to produce A2 minus. Okay. So actually I have 3 species, and we're going to separate them with lines, okay? So species H2A, species HA minus, and species A2 minus. Separated. There's an area where H2A predominates. In other words, it's the word predominates a little bit over here, but its concentration is greater than the other species. And here the concentration of HA minus is greater than the other 2 species. And in this area, the concentration of A2 minus is greater than the other species. So when is that the case? Well, directly. On this line of separation, put pKa1, and on this line of separation, put pKa2. And I'm going to tell you why. Because at pKa1, what do we have? Remember, at pKa1 in this buffer region, that's when H2A equals to HA minus. So that's when H2A equals HA minus. At pKa2 in this buffer region, that's when HA minus equals to A2 minus. Okay, those two species are equal. So anything, let's look at like this. Anything before this value, when the pH is less than pKa2, I have more HA, more of the acidic species. When the pH is greater than pKa2, I have more of the basic species. Okay? So if here they're equal to each other, as I become more basic, I'm going to get more A minus. If I go backwards, as I get more acidic, I'm going to get more HA. Here in this area, pKa1. As my pH becomes higher, okay, than pKa1, here's my pKa1. As my pH gets higher, so more OH, I get more and more HA species. As my pH goes lower, I will get more H2A species. Okay, so this is when they're equal to each other. More acidic, I get more of the acidic species. More basic than this pKa, I get more of the basic species. Okay? So that's very easy to draw, actually. It's not very complicated. What you do, put the species, put lines, then put pKa1, pKa2 to separate the species. It's as simple as that. So if I tell you, okay, that I'm at a particular pH value, so let's look at this as an example. Let me go backwards. And if I tell you that I am at pH equals to 9. And I ask you for this example, and I ask you for what species is the predominant species. Okay? So if you look at the titration curve, well, if we look at the titration curve and we actually have it, pKa2 is 9.7, pKa1 is 2.3. So at pH 9, I'm almost in this area here. So I'm in an area where HA is more than A2 minus. Okay? So I'm here. At pH 9, I'm right here. So I'm in an area where HA species predominates. Okay? Now, that's in the titration curve. What if I'm here? So again, just memorize 2.3, 9.7. If I sit there and draw this on a pKa scale, 2.3 here, 9.7 here, that's the pKa values, 2.3, 9.7. And if I'm at 9, where am I? This is 9.7, so I'm not higher, I'm at lower. I'm here. And it's greater than 2.3, so I'm still here automatically. Oh, lovely. The predominant species is HA. So this makes it very easy for me to tell which species is predominant. Better yet, do a third point here, which is when I have only HA minus in solution, only. Okay, so HA minus in solution. So HA minus in solution is at, that's when at my equivalence point, that's when I have half pKa1 plus pKa2. Do a calculation of that, and then you would actually see exactly what buffer region you should be considering. And we will look at a direct example of that, Because look, in this region where I have HA, I could have HA with H2A, or I can have HA with A2 minus, right? So here's my HA, remember. In the lower here, I have HA with H2A, and right above it, I have HA with A2 minus. So if you have this value point included, you could also see exactly which area you're in for more particular calculations. Now, sometimes you look at diagrams like this, which gives me my pH as my x-axis and the fraction of the species, okay, on my y-axis. And this just is a theoretical type diagram, which you could do an exact calculation of how much concentration of species you have. But the idea here is for us is theoretical, more or less. That initially I only have the H2A species. Here we have a diacid maximum. And then this H2A species starts to decrease until it's equal to the HA minus species. As this H2A is decreasing, the AHA species is increasing, which is in blue, until the point where they're both equal to each other. Then the HA species continues to increase. Usually, again, this concentration, we say that the number of moles is equal to the H2A, but in reality, we have alpha here, not concentration. In reality, it's not exactly equal. The HA then starts to decrease as the A2 minus is increasing. So my A2 minus is increasing, it's going to reach a maximum, but my HA species is decreasing. And so this intermediate, which is my HA species, actually eventually runs out completely, and there's nothing left in it in solution. It's an intermediate species. Also, my H2A will run out completely, and it's going to become 0. Okay. Everything gets converted into A2 minus. Okay. This is a di-base calculation. And when I have a di-base initially, if I look at the graph, it's going to be at a high pH, and then pH will decrease. And here I'm titrating an A2 minus with HCl, which is simply H3O plus. The A2 minus in the first part will be converted to HA because it will be protonated by the H3O plus. Then the HA will react further with the H3O plus to become A2 minus and water. It'll be neutralized further. So this is like 2 parts, remember, of a monobase. If it was a monobase, I would stop here. So instead, the HA now will react further with the acid and get protonated a second time. And so let's look at the shape of the graph. Indeed, I have 2 areas right here. Pretty much it should be more or less of straight, sharp decrease in pH. Well, here's a decrease in pH, and here's another sharp decrease in pH. So it's 2 decreases, sharp decreases in pH, which is usually indicative of a diprotic acid. And we can go ahead and do some pH calculations as we did with the other ones. At equivalence, we can always get the calculation, and we always know that immediately at half equivalence point, we have a pKa value because that's when HA minus is equal to A2 minus. Remember, I'm starting with an A2 minus, it's going to become HA minus. At some point in this buffer region, these 2 species are equal. That's at pKa2, which is right at the half equivalence point. What other point is direct, easy to draw? Yes, the 3/2 V equivalence. which is the second half after the equivalence point, another half equivalence after the first equivalence. Okay, and so here, once I have my HA produced in my solution, I am adding more H+, more H+ is added, and this HA is becoming H2A. At some point, they're equal to each other. When is that? That's at the second half equivalence. And that's at pKa1. Now notice, pKa2 starts first and then pKa1. Why? Because look at these two species, HA- with A2-. What dictates, what Ka dictates these two species? Yes, pKa2. And look at these two species, HA- with H2A. Which Ka dictates these two species? Yes, pKa1. Okay, so add equivalence. Let's look at the add equivalence. What do we have? We will have add equivalence HA- at the first equivalence, because all the A2- got converted to HA-. We have equal number of moles here. This becomes 0, 0. Everything gets converted to HA-. Once everything is in the HA-, what is this species? Yes, it's an amphoteric species. So the pH is simply equal to half pKa2 plus pKa1, which it doesn't really matter which order you put it in. Then, well, that's my initial concentration. Let's see. We're just saying that here we have Henderson and another Henderson. When I have my H- with H2A, we have another Henderson. And when they're equal to each other, of course, these two concentrations, you get the pH is pKa2. We already said that. Okay, now we're at the second half equivalence here, where what species do I have? Everything now, I have HA2 equal to H2A. And now as I become more and more acidic, I get more HA until all the more H2A, until all the HA has run out and everything gets converted to H2A in my solution. So what's the pH of this? This is just the normal pH of a diacid, which can be treated as a simple monoacid. And if the concentration of that monoacid is greater than 100 pKa1, Ka1, then we use pH equals half pKa1 minus half the concentration of that acid. Now we do have to watch out. We can't always use this. We sometimes have to use a quadratic, so watch out. And a lot of times that happens actually. This is an example of a diacid, which is sodium carbonate with HCl. So tell me what we can distinguish right away. Yes, here is my first equivalence at a straight line. I have two sharp decreases, and it's decreasing, and so therefore this is a di-base titration. What direct pKa values can I right away put, or pH values can I put? Yes, if this is at the equivalence at 1, and at 2, surely, which is 2 times the first equivalence, is going to be my second equivalence. Again, here we have moles of HCl, but it doesn't really matter. Volume versus moles versus X. What you have as the X, as long as it's considered amount of the HCl added. If we have here half equivalence, at half equivalence, what is the pH? Yes, that's equal to pKa2. So that's going to be pKa2, which is 10.32. What else, what other value can I put right away? Yes, indeed, at the half equivalence, which is pKa1, which is 6.34. Also, this is a very easy one to put in, the hydrogen carbonate, because that's an amphoteric substance, and the pH is simply half pKa1 plus pKa2, or pKa2 plus pKa1. So that's easy to calculate. A little harder to calculate, of course, is my initial concentration and my concentration at the second equivalence, because I have to actually do the calculation for the concentration of the species in my solution. The other three values, you don't need concentration terms.